Today's class will be on feature engineering. This is course 3 of Technology Fundamentals, session 1, right here at the beginning of the week. In the previous session, we talked about model pipelines and conveniently began with a suitable set of input data. In the real world, this is hardly ever the case. What is constant is this: at the end of the day, our models need numbers. Not only this, but a suitable set of numbers. What does that mean? That will be the context of today's session, feature engineering, putting in relevant numerical data for our model. All right, doing some standard imports here. We should recognize most of these. Nothing new. We will be spending time on a few sklearn pre-processing techniques today. So there's the one-hot encoder there, as well as some methods for detecting collinearity. All right, and our data sets for the day. This margin data we'll recognize from our data hunt 2 last week. Okay. We also have the same information, except now the order dates have been unpivoted from what was originally the date column. All right, so now for each date that appears in the column header, we have an associated number of kilograms for the order. Let's look at this one, 53770. You can see that's the first order in the margin data frame. So same information, except one has the orders dates in a singular column. We call this a tidy data set, this margin data, and here it's unpivoted. And we have also dropped the EBITDA per kilogram column in the orders data frame. All right, categorical features. So we'll be starting with two different things that we're going to look at. The first is derived features, and categorical features is sort of included in that. And then transformed features. So this is kind of the bifurcation of today's session. All right, at the end of the day, our algorithms operate on numerical values. How do you get from a series of string values to numerical ones? And let's take our customer column as an example for this session on categorical features. So in our customer column, we have what looks like 6 unique string values: Slugworth, Perca-Cola, Fickelgruber, Zebra Bar, and Dandy's Candies. A naive way to extrapolate from these strings to numerical value entries would be to just assign a number to each string. So 1 for Slugworth, 2 for Perca-Cola, 3 for Dandy's Candies, and so on. But the issue with this is that we would inadvertently end up with some weird mathematical relationships between these variables. For example, Dandy's Candies minus Perca-Cola would equal Slugworth. We don't really want this to happen. So a workaround for this is to think multidimensionally. We express our categorical values as vectors in a hyperspace where they cannot be expressed in terms of one another. In other words, they are orthogonal in this space. So taking the same 3 strings now, we could represent Slugworth with a vector of 1, 0, 0, Perca-Cola with 0, 1, 0, and Dandy's Candies as 0, 0, 1. So they're in this 3-dimensional space, and we can't express any one in terms of the other because there is no linear transformation of, say, the Slugworth vector that we could do to get the Perca-Cola vector. All right, in machine learning vernacular, such a scheme is called one-hot encoding. Now, sklearn has a couple useful libraries for one-hot encoding. We're going to use the one-hot encoder class from its pre-processing library. So I'm importing it here. We're going to interact with one-hot encoder the same way we do, for the most part, with some of the packages we've seen out of sklearn already. The model packages like linear and logistic regression, as well as lasso. We're going to establish a new object, okay, from the one-hot encoder blueprint. We're going to call it ENC here. We're going to grab the categorical columns that we want to convert from strings to numbers. I'm going to store it under the variable name xcat. So all the customer entries will be stored in this variable, and then I'm going to fit this encoder to this data. After fitting our encoder, we then use this object to create our new training array. All right, and I'm just going to display some of the in-between steps so we can see what's going on. So here's our original x underscore CAT object with the customer names. All right, so I'm just printing that out. And now I'm going to transform from using my ENC object. I'm going to call the transform method, feed in the categorical data, take the output of that, put it into an array, and store that under the new variable name oneHotLabels. Now I'm going to print out the oneHotLabels. First, I'm going to show the shape of that object and then the actual labels themselves. So here's the original data. All right, and it has a shape of 1,668 unique entries. The new data object, the new array, has the same number of entries, but now the second dimension has 5 unique elements in it. And here is the output from that. So indeed, we can see that every customer is represented by a unique vector that is orthogonal to the vectors that describe the other customers. All right, we have our customer information one-hot encoded. We need to do this for all our variables and concatenate them with our regular numerical variables in our original data frame. So again, I'm going to call one-hot encoder blueprint, set it to an object, and this time for my xcat, I'm going to pull all of the categorical columns. I'm going to first fit my object and then use the transform method within my object to create the actual one-hot-labels. And now, when I look at the shape of my complete data frame, which includes both the numerical values, in this case there's only one numerical value, and that's the kilograms column, and the one-hot-labels, I now have 119 columns, right? So all of those columns that initially had strings in them have been converted into vectors, and so our dimension along the feature axis becomes quite large. So that is going to be all my X data. My Y data is going to be the EBITDA per kilogram column. And now we have an exercise. Using the X and Y data sets, use train test split and linear regression to make a baseline model that is based on what we've learned so far. Assess your model performance visually by plotting Y-test and Y-test pred. Okay, so I've got what looks like my imports already written for me. That's really nifty. And I'm going to call train test split. All right, and I'm going to feed it my data. So I think I stored this under X, capital X, lowercase y. All right, looks like I'm getting some output arrays. I know that the parameter here is going to be something like train size, I think. Let's try that, train size 0.8. Also random seed, something we might want to set, or random state. Random state, I believe, is the parameter name. Let's try that. Cool, and I'm going to store the output. So I know the first one's going to be X train, and then it's going to be X test, and then Y train and Y test. Very nice. All right, so I have my train and test sets. So now I'm going to do, I'm going to make a model. Model equals linear regression. And then we'll do model.fit X train, Y train. Let's make sure this runs so far. Okay, it does. And then we'll do Y test pred equals model.predict on X test. And then we'll just do a simple plot. We'll do plot.plot. What does it ask for? It says Y test versus Y test pred. So Y test pred will be on X. All right, we'll set the line style to an empty string and then marker to a point. All right, not too shabby, not too shabby. Question, how can we assess the relative feature importance of the features in our model? All right, so it's just a thought question, it looks like. We could be tempted to inspect the coefficients, right? So those are stored under linear.coef. In my case, we called it model, so it would be model.coef, right? We can see the coefficients in front of every feature column. So we'd be tempted to inspect that, but of our model to evaluate the relative feature importance. But in order to do this, our features need to be scaled. And that is so that the relative coefficient sizes are meaningful, right? If we have some feature vector that spans from, say, 1,000 to 2,000 in just hard number values, and another column that is from 0.01 to 0.1, the coefficients in front of each one of those columns would be scaled with the raw number values, right? So that would not be comparing apples to apples. So that's why we would want to scale and center our features. What other issues might there be? Think categorical versus continuous variables. Okay, so on that subject, let's take, for example, what we just created. So what you had in X was a mixture of those one hot labels, right, containing zeros and ones, but we also had one column that contained just floating point values. That was the kilogram column, right? And so when we're going to compare the relative importance based on the coefficients in the linear model, we have to recognize that the one hot label coefficients are going to operate on the basis of just turning them on and off, right? Because wherever there's a one, that column is on, and whenever there's a zero, that column is off. And so the coefficients in front of there are going to be operatively different than the coefficients in front of the floating point feature columns, like the kilogram column. So I want to keep that in mind when we're looking to interpret this model. So that was just like a little thought game for us. So I put categorical features in sort of its own section here, but perhaps it would be under derived features. This is the main bifurcation I like to talk about when discussing pre-processing data is between derived and transformed features. So we're going to cover transformed features later, but first let's talk about derived. Can we recall an example of where we've seen this previously? That's right. Earlier on in our first session, we derived some polynomial features to create our polynomial model using the linear regression class in sklearn. So that was on Thursday when we had our bias variance trade-off conversation, and we were working with a polynomial model. And when we went to do this, we actually did it in two steps. We first created the polynomial features, and then we fit them with linear regression. So we just had a cursory glance at that on Thursday. Here, we're going to spend more time. I've also got just an example here for people who might come from an engineering background. We actually see this a lot in engineering, where we will describe log relationships or some other transformation of the original variable. Actually, let me see if I can find this in my Bird, Stewart, and Lightfoot book. So this is a chemical engineering textbook, a classic textbook, and we're just showing that when we're discussing diffusion rates inside of a continuous stirred tank reactor, we often look at ratios rather than the actual diffusion coefficients themselves, all right? And maybe some of us can think of other examples where we've derived features in our physical sciences. But the idea here is that we're going to take some idea, some domain area expertise, and use that to engineer our own features before feeding them into the model. Let's revisit our example from the previous session, right before we introduced grid search and sklearn. So again, this is from last Thursday. We import polynomial features from the pre-processing library, as well as the linear regression model from the linear models library, and make pipeline from the pipeline library. So all this code is a repeat from Thursday, right? So I'm making a pipeline for my model, starting with first engineering the features and then actually finding the coefficients in front of them. In the above, we used sklearn's convenient tool make pipeline to join together the pre-processing tool polynomial features and the basic model linear regression. Let's take a look at what polynomial features does to some simple data. All right, so I'm just going to make some x values. They're going to range from 1 to 10. And then my y, or my target values, are just going to be x cubed. And so I'm printing out x and y. So here's my target values, and here's my x. If I wanted to create my features to eventually feed into my linear regression model, I would first have to engineer them with polynomial features. I tell it the degree. I'm going to go up to the third degree because my target is up to the third degree. And now I'm going to create a new x where I'm taking that object that I've used for creating polynomial features and fitting to my x data. So right, I'm calling the object, calling the fit transform method on the original x data to create the output array. We see our new feature set contains our original features plus new features up to the nth degree, in this case the third degree polynomial we set when creating the features object from polynomial features. So here's x2, this is what we just created. We have, what is this column? This column is x to the 0, right? And then we have x to the 1, 2, and 3. Now that I have my features, I then create my model. And here I'm doing a little bit of shorthand. Typically, we've seen this broken up into two different steps, but here in a single step, I'm calling the blueprint and then fitting my new engineered features and my target value to that object. Y hat, sometimes I'll call this Y pred, right? So this is just the predicted values, and then I'm doing a scatter plot. So we have a plot of X versus the predicted Y. What did I do here? This is actually something that we haven't discussed before. So X and Y, these are my raw data values. And then I'm just also plotting my line to represent the predicted values. Cool. Dealing with time series data. This can be a big subject in machine learning, and here we're just going to spend a little bit of time on it. Often we will be dealing with time series data, whether it's data generated by machinery, reactors, or by our customers or our sales representatives. In the following, we discuss some simple practices for dealing with time series data. If you come from an engineering background, this might be interesting to you. I've left it here as an enrichment. If you want to dig into this section, you can. But fast Fourier transforms, in a nutshell, is a way for us to go from time space to frequency space. So if we're observing some kind of oscillatory behavior in our data, maybe it's helpful to map then into a frequency space. All right, so this is here for you if you want to peruse it, but we're not going to spend any time on it today. But that's just one other way of dealing with time-based data that might have some oscillations in it. What we will spend time on is rolling windows. One powerful technique for dealing with time series data is to create a rolling window of features based on the historical data. The proper window size can usually be determined by trial and error or constraints around access to the data itself. So sometimes our window sizes might be dictated based on the granularity that we have in the time dimension, the amount of data that we have going back in time, right? So this may dictate what we're able to do. In the above Jiffy or GIF, we have a window size of 7, as are represented by the dark blue boxes. What that means is for whatever time step units we are in, and that could be minutes, days, months, etc., we will have 7 of those time steps included in a single instance or observation. This instance or observation is then interpreted by our model and used to assess the target value, which is typically the quantity in the very next time step after the window, and that's the green bar in this GIF. So we're going to do an exercise here. For this exercise, you will use the process data function below to help you optimize the window size for predicting the order quantity in any given month. We'll create a model using a window size of 3 and predict the order quantity for the month immediately following the window. Create a model for window sizes 1 through 11 and report the R-squared for each model. So we have this handy dandy function here built for us. I'll go ahead and read the doc string and explain a little bit, but we're not going to worry too much about how the underpinnings of this work. So it looks like this function splits your time series data into the proper windows. Parameters are x, y. This is an array, right? This is an array, not a data frame, of the input data. If there are non-time series columns, it assumes they are on the left and time columns are on the right. Next parameter, time underscore calls, is an integer. This is the number of time columns. The default is 12. Window, also an integer. This is the window size for the time data. The default is 3. Returns x underscore is an array. The independent variables includes time and non-time series columns with the new window. Y underscore is an array. The dependent variable selected from the time columns at the end of the window. So it looks like this is automatically going to do what we're asked to do here, create a window size and predict the order quantity of the month immediately following the window. And then we have this thing called labels. The time series labels can be used for subsequent plotting. All right, and we have a little bit of documentation here for us to read if we're interested. All right, so it says use data and the function process data to create your XY arrays, then use train test split to create train and test portions. So here's data, it's written for us. It looks like it's just going into orders, right? So here's orders, and it's pulling out the values. So this helps us turn it into an array, and I'm just grabbing all of the rows and then only everything after the first 6 columns. So only the time data, right? Going back to orders, it's only grabbing everything after customer. We're dropping the one hot encoded labels that or the rather the categorical columns. So we're making a predictive model that only uses historical kilograms. We're not using any of the metadata associated with the order. That's interesting to note, okay? Use y-test and y-pred for your actual and true test data. Name your labels for the test set labels test. Change only window parameter and process data. Okay, so first we need to call process data. Remember that's going to return x, y, and labels. And we'll call this x. Yeah, I'll call x, y, labels. That's fine. And we'll do process data. And here we're going to feed in data. And we only have to change window, so I'm going to go ahead and put that as the default, and then we'll see if this runs. All right, seems to be doing fine. Now we're going to do x train, x test, y train, y test. It should start to feel really familiar to us. Train test split, and we'll feed in x, y. Train size can be 0.8, and we'll do random state 42. And model will equal linear regression model, and we'll do model.fit x train y train, and then y-pred will be model.predict x test. All right, seems to run fine, and now we'll run this down here. All right, so it looks like this function gets our r squared for us. That's cool. And then we're looking at the predicted versus the actual values. All right. Notice I had this labels thing here. So quick note on that. If I wanted to use the labels, I could do the following. We could do model.train on x and y, and then predict on x. Oh, excuse me, model.fit, right? Model.fit, and all right. And so we'll call y test is just going to be y, and then we could run this again, and we could do hover data equals labels, all right? Shoot. What have we here? String or interlinear possible. Well, we will not worry about this, I think. Let's see, maybe try one more thing. Had a nifty little tool here for viewing for viewing the X data that was used to make the prediction, but I think we're just going to let this one go. Labels. Yeah, unfortunate. So there's a way with Plotly Express to display these values. So these would be the values from the window. So it's just interesting to note. We'll go ahead and ignore that request for now. All right, let's try one more thing. Hover label. Is it labels? Hover labels. Nope, not hover labels. All right. We'll let this go. In any case, we're seeing a plot of our predicted versus our actual values. And our objective here is to figure out what the performance is for different window sizes. So one way we could do that is to write a for loop and then change our parameter here to range from 1 to 11. So that's the second task. We'll leave that for you guys to do outside of this session. All right, image pre-processing. Image pre-processing is beyond the scope of this session for today. We're going to dedicate time to that in the 4th week of the course, all right, when we actually get into computer vision. Just know for now that there's a wealth of considerations for how to handle images, and they all fit within the realm of feature engineering. All right, and that concludes our section on derived features. Again, depending on what your application is, A lot of stuff can fall under derived features. This is simply where you're taking some kind of domain area knowledge, something that you know about the data that you would like to embed as a feature vector when you go to actually train your model. So that's that. In contrast, transform features are features that we would like to augment based on their relationship within their own distribution or to other distributions within the data of our training set. In other words, we're not deriving new features based on some empirical knowledge of the data. Rather, we are changing them due to statistical properties that we can assess based on the data itself. Funny little picture here. Sorry, the quality level of our sample of students was 2 standard deviations below the mean. We were skewed from the beginning. Very nice. Skewed data can lead to imbalances in our model prediction. Why is that? Skewed values in the distribution will bias the mean. When assigning weights to this input feature, therefore, the model will give preferential treatment to those values that skew the mean. To demonstrate, I'm going to use SciPy to create some skewed data. So we should familiar ourselves with the stats library within SciPy. It'll be pretty useful for us. For this, I'm importing a function that will allow me to pull and sample data from a skewed normal distribution. All right, so here it is. A is just a hyperparameter that we can vary to decide on the actual level of skewedness, right? So as I move this higher and higher, I get more and more skewed data. We can now generate a random population based on this distribution, and I'm going to do that with the random, RVS stands for random variable sampling or something like this, but in any case, it's going to allow me to sample a bunch of numbers from the probability distribution, in this case 1,000 of them. Now I'm just plotting a histogram of those values. Unskewed data will return something close to 0 from calling df.skew. When dealing with actual data, we can use df.skew to determine whether we should transform our data. So remember, we first saw this, I believe, in our session on regression. Should be like the beginning of last week. And so we'll recognize that here. So as I call .skew, I'm seeing I get a pretty high number, something a lot bigger than 0 in any case. There are a handful of ways to deal with skewed data. We can log transform the feature vector, we can square root transform it, or we can box-cox transform. And we're going to start with just the first two. Talk about box-cox in a later moment. Here, so the original data set has a score of 106. Square root has a, again, this score is the skewness, .skew. So there's our original skewness, 106, goes down to 0.16. Log gets a little hairy at -121. We can't take log 0 we can't take the log of 0, right? So that's going to be something that is going to affect this. We didn't get an error message here, even though we had log 0 values, though, because it just ignores those values. In any case, box plot is often a good route to go. Not box plot, box cox. Box cox is often a good route to go, but it has the added restriction that the data has to all be above 0. So now we're going to do the same thing again, but we're going to add the restriction that all the data is above 0. So that's what I'm doing here on line 3. So here's our data set. And now I'm doing the same exact thing, but also doing box cox. So original skewness at around 0.98, square root 0.13, log -1, and box cox pretty close to 0 at -0.06. And that's that red histogram there. So box cox does a pretty good job. We don't need to get into the nitty-gritty of box cox. Just know that it's algorithmic. So there's a series of steps that you perform on the data to get it box cox transformed. It's not a simple mathematical operation. It's an actual algorithm. So we'll leave it at that. Our exercise, repeat section 231, this time synthesizing data from a gamma distribution and transforming it. Which transformation best reduces the skew? Do this for a data set that does not contain values at or below 0. So there's gamma. And I'm just going to take my formula from our skew norm. All right, so I'm just going to take this and the API is going to be exactly the same. I'm just going to have gamma.rbs. So there's R, and now I can just take the code from what we did previously and create a data frame from R and look at the performance here. So the original skewness 0.8, square root 0.3, log 0.24, and Boxcox at 0.01. So again, Boxcox really takes the cake for creating a transformed data set that is really, really unskewed, very, very centered data. All right. Now on to collinearity. Collinearity can also affect the performance of your machine learning model. In particular, if features are collinear, it can be easy for your model to overfit to your training data set. This is often mitigated by regularization, right? So we talked about that a little bit with Lasso, ElasticNet, and ridge regression. If you're curious, you can read more about it. I have a link here to Stack Exchange. We will still explore it explicitly here by calculating the variance inflation factor on some hypothetical data. So VIF, this is defined as 1 over 1 minus r squared. We should recognize r squared, right? So this is 1 minus RSS over TSS. And if we're calculating RSS, the residual sum of squares, what does that cue to us? That cues to us that there's some model prediction of the target variable. So what is VIF? VIF is simply, all it is creating a linear regression based on all of the independent variables and looking at how well the model does at predicting one of the independent variables that we happen to be looking at. So let's just take an example. Let's take an example. Importing variance inflation factor from stats models. And in order to do this, I'm going to make up some data. All right, so I'm going to have x naught values that range from 0 to 100. So that appears on x here. x1 is going to be based on my function I've defined. And it looks like I'm just doing the square root of x plus some noise. So for x1, I have a little bit of noise, not a very little amount. x2, slightly more noise. And x3 is just going to be random integer values from 0 to 100. So no real correlation with x naught. And hence no, conceivably no correlation with x1 and x2. All right, so there's my data, right? x1, 2, and 3, x naught is just the x-axis. To calculate the collinearities, I'm going to aggregate these x's into a data frame. All right, so I'm just taking those arrays, and now I've got one column for each feature. Remember, x1 and x2 are somewhat defined by x naught. x3 is totally random. x2 has more noise than x1. And now I'm going to call upon the variance inflation factor method, feeding in my data frame values, plus the data that I'm going to use as the target value for each one of the models that I create. All right, so looping through here and now displaying the results. So what we're seeing on the features column is that for each one of these models, this feature was left as the target and removed from the independent variables. All right, and so the VIF is an indication of that resultant model performance. If we get a really high VIF, those independent variables were really good at predicting the indicated feature, meaning there might be some degree of collinearity in the models with the indicated feature. So in this case, we're seeing x naught, really high score, and x1, really high score, which makes sense, right? X naught and x1 are very closely related to each other, and they're also, to some degree, closely related to x2. What might be surprising is that x3 has a higher VIF than x2. In any case, the usual cutoff for concern is around 5. We usually want a VIF factor below 5. If it's below 5, there's no collinearity. Fixing collinearity. It is good to acknowledge where collinearity exists, as this will influence the interpretability of your model. In most cases, however, it won't have a heavy influence on the performance of your model. A simple method of dealing with collinearity is to remove the highest VIF features from your model iteratively, assessing the performance and determining whether to keep the variable or not. Another method is to create some linear combination of the correlated variables. This is encapsulated in the section on dimensionality reduction. All right, so we're not going to talk about dimensionality reduction in this notebook. It's actually left as a enrichment topic for you all. All right, normalization. Many learning algorithms require zero mean and unit variance to behave optimally. sklearn preprocessing library contains a very useful class, standard scaler, for handling this automatically for us. So I'm importing standard scaler from the preprocessing library. And again, as we'll see with a lot of the blueprints in sklearn, I'm going to set this to a new object. I'm going to call it scalar. Then after I have the object declared, I'm going to fit transform to my data, and I'm going to store this under a new variable called normed. So here's my original data. My original data plotted in a kernel density estimate, right? So we see that it's these distributions are not centered around 0. They have weird dips and rivets in their actual distribution profiles, and they do not have unit variance. The scaled and centered data will have unit variance, so the standard deviation is 1 and the mean is 0. We still have those dips though, however. All right, so standard scaler only centers the mean and turns the standard deviation to unity. Exercise, normalization effect on VIF. In the above, we saw how to scale and center variables. How does this affect the variance inflation factor? Calculate the VIF for the raw and scaled / centered data. So let's first take the VIF for the raw data. And we can just take this code from up here, display VIF. I'm going to do the same thing again now. And we're just going to copy these, but doing it on the normalized data. So again, just to be explicit, I'm going to actually just do this again so we can see the steps here. So now I'm taking standard scaler and fitting and transforming colon, and now I'm going to do normed.values instead of colon.values. I don't need to do values because it's already an array. And here we see there actually is a slight effect on what VIF returns. I'll leave it as an exercise for you all to think about that. All right, so this is the variance inflation factor for the variables as they were before, and now scaled and centered. We saw a change there. Dimensionality reduction. Dimensionality reduction is an awesome way to do feature engineering. It is very commonly used. Because it is also an unsupervised machine learning technique, we will visit this topic in that section. Again, this is actually going to be an enrichment topic for you all. So the notebook for dimensionality reduction is going to be in the notebook called unsupervised learning. Last topic here, missing data. We will often have missing data in our data sets. How do we deal with this? Let's start by making some data with missing data. We'll use a NumPy NaN data type to do this. So I'm importing the NaN data type from NumPy, and I'm filling in some NaNs in my data set. So I have X and Y here. One of the most standard ways to deal with this is imputation. All right. This is based on statistical descriptions of the feature column. So we can impute either on mode, median, or mean. And we can do this with simple imputer from sklearn. So when I declare my object from the simple imputer blueprint, I select the strategy. So here I'm doing a strategy based on mean. And then when I impute using the fit transform method on the original data, we'll see that all of the missing values are filled based on mean. So let's also print X. So we'll see X. So we had this top left and this second from the bottom. So 5 and 4.5 here have been filled in. So 5 is going to be the mean of that column, and 4.5 is going to be the mean of that column. We can change the strategy to median, for instance. And now those numbers are based on the median. And we can also do mode. Mode. Most frequent. Oh, that's right. I got a little note there. Most frequent. All right, so 3 and then 0. And it looks like, so look at this column here. So we have 0, 7, 5, and 8. So it looks like it just defaulted to, if there was no frequent It just chose the first number that it saw in the column. So it's an interesting behavior there. All right, other strategies. Depending on the severity of missing data, you will sometimes opt to remove the whole column or perhaps apply some simple learning to fill in the missing data. Simple learning here, I mean create a simple machine learning model to fill in the missing data. This is a great article on more advanced strategies for handling missing data. All right, that is it. Thank you for listening in.